Kohn. He is a Silver Professor of Mathematics at the Courant Institute. He did his PhD work at Princeton, and then he continued on Courant as an NSF postdoc. And then after his NSF postdoc, he joined the faculty and has been there since. If he allows me, I would like to say, in the tradition of the Courant Institute, his work maybe could be described as applied rigorous mathematics. And he is both an AMS and SIAM fellow. He has given plenary talks at the ICM and ICIM, so the pure and the applied side of both societies. So lastly, I would like to say he was recently elected to the American Academy of Arts and Sciences. So thanks.
Thank you very much. It's a great pleasure to be here, and I've had a very interesting day so far. You all ordered beautiful weather. Okay, so I have a small confession to make about my title, which is that there's some exciting material about wrinkling that I folded into my talk, and the folds were almost completely eliminated in the process. It's more about wrinkling than about folds. Okay, so this talk is about thin elastic sheets. It's about wrinkle patterns and an attempt to understand them using mathematics. But at the end of the day, it's also about the idea that thinking about pattern formation problems like this is a current challenge in the calculus of variations. My viewpoint will be to focus on these pattern formation problems as calculus of variations problems. I think you've all had some exposure to the calculus of variations. You would know that its roots are very deep into physics and geometry. In geometry, we think about geodesics. In physics, we think about action minimization as a viewpoint on understanding Hamiltonian dynamics. We also think about soap films being modeled as area minimizing surfaces, though if you know something about soap films, you know that that's, in fact, an imperfect approximation. The theory of harmonic maps has very strong connections with liquid crystals. So wrinkling is somehow in the same vein, an area where physics and physical phenomena challenge the calculus of variations. So what it has in common is that we're thinking about, I'm going to talk about problems that come from physics and mechanics. Also that it's problems where we're talking about real phenomena, some more familiar than others. It's a little different because in thinking about geodesics, thinking about soap films, thinking about many problems in the calculus of variations, you've got a variational problem. You're thinking about its minimizers or local minimizers or critical points. Here we're going to be talking about patterns. Oh, that's not the usual thing, right? That's different. At some level, from a mathematical viewpoint, we're talking about families of patterns that really come from thinking about sheets that are thinner and thinner, and where there's some sort of weak convergence, not strong convergence, about what you see. These pictures, by the way, just sort of some sense of what do I mean? How is it that patterns show up as wrinkling or folding? The one in the middle should be probably the most familiar. It's lifted from a physics paper, but it's really just about drapes that are hung at the top, of course, in the usual oscillatory pattern. And you'll still see, you would usually call those folds, but maybe I would call them wrinkles at the bottom, but with a different length scale. gravity's pulling them down. Bending resistance is preferring a coarser scale at the bottom. There's some sort of energetic cost to coarsening, and you get this pattern. That's one of the examples I won't talk about today because it's squeezed out for more recent ones. Here, this is a classic experiment. Modeling it was, models based on it by Mahadevan and Serta were sort of the early history of this kind of subject. It was done by taking an elastic band such as you might have used in an exercise class and attach rulers at both sides, pull, and you see that. And then the question is, oh, what sets the length scale here? What's happening when the wrinkles sort of disappear? Over here instead, I will be talking about the picture on the right in some detail. And there, what's envisioned is a thin elastic sheet. OK, you all know that if you try to wrap an apple with saran wrap, the saran wrap wanted to be flat, then something, it doesn't work that well, right? Well, it works OK. You can wrap an apple. If you wrap something with very large, it's almost flat, only a little bit of curvature, it'll still be the case that a naturally flat sheet will have to wrinkle because the circumference is mapping to a circle that's too small. So that's another type of wrinkling. Anyway, our goal is to think a little bit about problems like that. Why is this not clicking? Okay, so I think I've already more or less said this. So wrinkling, so don't understand it in a vacuum. It's not. So the point here is wrinkling. There's easy to observe, easy to do experiments on. There's plenty of physics literature. People do, in that community, think about how to design things that will wrinkle in controllable ways, and in order to maybe use those wrinkles, or to try to simply observe what happens and use that as a way of deducing the properties of the sheet. But besides that, pattern formation in liquid crystals, ferromagnets, Martensitic phase transformation, a whole bunch of other physics problems share a similar mathematical structure. And so thinking about this as a calculus variations problem is about thinking about, oh, let's try to experiment with how we can do things in this setting. What's the structure? Well, I'll spend some time on this, but basically the elastic energy is very non-convex. The point in common with these physics applications is that thinking about thin elastic sheets is similar to what a physicist would call studying a Landau theory. OK, we'll get to equations soon, but still sort of staying at the top. If you approach these things as calculus variations problems, I just told you it's very non-convex variational problem. I'm going to take the idea that, oh, maybe the patterns we see, well, physics would require them to be stable local minima. I'm going to suggest maybe they're more or less, maybe they're more or less the ground state, the global minimum. I mean, would you imagine that's true? Well, it's a bit like the fact that atoms form crystals. Oh, really, they form crystals with defects or polycrystals. But the fact that atoms like to be arranged in a crystalline way is like a leading order approximation to what you might see. So that's somehow the conjecture that my work is exploring with respect to wrinkling patterns. And then you would say, oh, is it true? Well, if it's not true, that's interesting too. But in order to know whether that's even true or not, we need to know what would be the energy minimizing patterns. OK. Now, in practice, okay, nature shows us patterns. So you can imagine what happens when you plug that pattern into the variational problem. Think of that as minimizing the variational problem within an ansatz. If you want to know whether you got the ground state, then you have to ask the question, oh, yeah, but is that an energy minimizing pattern, at least approximately? Yes?
What's an ansatz?
What
is an ansatz?
What is?
An ansatz. A-N-S-A-T-Z.
Ansatz. Ansatz. A trial function for the variational principle. And so minimizing within some finite, tuning parameters within some overall picture. That's what I mean by an ansatz. That would give an upper bound because we're studying the calculus of variations. The real conceptual challenge is to find lower bounds. In a convex setting, you would use convex duality, but we're not in a convex setting. And then, of course, upper bounds and lower bounds feed on one another because one sometimes finds that the picture that was first conjectured doesn't meet the lower bound, and then one or the other has to be improved. So that's the kind of story. And so I'm going to tell you about this story. This, if you wish, is not really, it's not my style to try to give you a big picture summary of this area. There's too much to say about that. Instead, I'm trying to give you a story which I think is interesting, which, of course, I have to give you some background. I'll zoom in on some work I did with Huimin Nguyen in 2013. Then that picture I already showed you briefly is associated with the story with Peter Bella that's pretty recent. And then my final story, which I'll try to reserve a fair amount of time for, is work by my former student Ian Tabasco, which I think is a very special achievement and worth dwelling on for a while. Okay, so finally we get some math. So I like to start by thinking about paper, because paper is already very familiar. When you talk about, so paper is a thin sheet. It doesn't stretch very well. It doesn't compress very happily either. It'll buckle instead. Okay, so some elastic sheets, like say Saran wrap, are a little more willing to stretch. But anyway, if we're going to represent a thin elastic sheet, it's got a reference shape which might be flat. If it's naturally flat, then it's represented by a region in the plane, and you're going to map that region to R3. Okay, so its configuration is a map from a region in R2 to R3. The elastic energy has two parts. The first part is the resistance to stretching. And the second part is the resistance to bending. And of course, let's see. If I take a sheet of paper, that's the left-hand figure up there. Its configuration in that familiar environment is I'm holding it. It's being pulled down by gravity, but it doesn't hang straight down. It forms an arc that's determined by the competition between gravity and bending resistance, given that it doesn't stretch. Mobius band is a similar story. Okay, mathematically, this sense that it doesn't stretch, if it were truly an isometry, then this map G, its deformation gradient dg, differential dg, would be an isometry from R2 to R3. If it were to stretch, the principal stretches are associated with the eigenvalues of the symmetry. You take the dg, you take its polar decomposition, and the symmetric part of that has eigenvalues, and they represent the stretches. So the membrane energy is proportional to thickness, though sometimes I'll normalize that. And the integrand is something that tests how much you're not in isometry. Bending energy, it really has the same origin. Your thin elastic sheet, even if the midplane is an isometry, if the midplane curves, then the upper and lower edges can't be isometries. The upper edge will be stretched a little bit. The lower edge will be shrunk a little bit. That effect is proportional to curvature, and the extent of it is proportional to distance from the midplane. So the membrane energy of the upper and lower edges, you might say, they wind up being associated with curvature squared. That picture is two-dimensional, but for a two-dimensional sheet in R3, you'll have two principal curvatures. And the bending energy is small because it's the midplane doesn't experience it. It's only the levels parallel to the midplane, so it's of order h cubed. In other words, it's smaller by a factor of h squared than the membrane effect. Okay, so we combine these two. Of course, if there's gravity or something, we'll have to add something about that. And you have this membrane term is very non-convex. It has plenty of preferred states, but they don't form a convex set. They're the isometries. And you have this higher order regularizing singular perturbation, which is the bending resistance. And the relationship between what I'm going to tell you and other pattern formation problems from physics involving ferromagnets or liquid crystals or phase transformations in solids really comes from the fact that all those problems have a non-convex term and a higher order singular perturbation, but different order parameters, you would say in the physics language. You're studying strains or gradients or various kinds of curl-free fields, divergence-free fields, different types of ways of representing the unknown. This is an applied math department. The first thing you normally do when you study a problem is non-dimensionalize it. So let me come clean on this. When you non-dimensionalize this problem, the shape of the sheet gets replaced by some normalized shape of the sheet, and the thickness gets replaced by the non-dimensional thickness. That's the true thickness divided by lateral extent. Okay. Now, if you're studying a Mobius band, or maybe the sort of conical configuration that I easily form with a piece of paper, you're going to need a geometrically nonlinear viewpoint, a viewpoint that accepts that large rotations will be seen. But if you're studying wrinkling, then you can capture the essential physics with a small slope approximation. And even though the configurations we see, for example, in hanging grapes are not always small slope, I'm going to stick today with a small slope approximation. So how does that work? Let's separate the in-plane displacement and the out-of-plane displacement. Let's see. So in these right-hand two pictures, center and right, the out-of-plane displacement means it's coming out of the board, out of the screen. And okay, and then in terms of those, the small slope approximation, the membrane and bending energies look like this. The membrane energy, which measures lack of isometry, becomes the in-plane linear elastic strain plus this. This is the rank 1 tensor that's made out of the gradient of the out-of-plane strain. And then the bending term feels the second gradient of the out-of-plane strain. Now, okay, the bending energy shouldn't surprise you too much. When you teach calculus, I'm sure you teach your students that if you're studying the graph of a function, its second derivatives let you know the quadratic approximation, and in particular, the curvature of the graph above its tangent plane. So, but the first one, if you're not in this area, that's going to look a little strange. So let's talk about where that comes from. Pardon me?
In the previous slide, E of U was linear in U. Is that just a missing?
No, that's right. So this guy here is the linear strain. So this is linear in U, but quadratic in W. And, okay. So where does that come from? All right. So, of course, so I told you it's going to be a small slope approximation. So in a fully nonlinear framework, I'm thinking my sheet is the x1, x2 plane. x3 is equal to 0. And points are going to be moved to some nearby location. U1 and U2 were the elastic displacements in the plane. Oh, and it's going to come out of the plane. So W, so this third one is 0 plus W. Okay? And now you substitute that into my nonlinear theory, and you assume that gradient of U and gradient of W are small, and you get what I said before, but let's actually do that. Let's see what's involved. Okay, so a little simpler. Instead of a two-dimensional sheet deforming in R3, let's take a one-dimensional string deforming in the plane. So it's equivalent to considering a sheet that deforms only, that stays uniform in the third direction. And, oh, good. So now the reference domain is just a line segment. And there's just one in-plane displacement, call it U1. It's a function only of the reference position x1. The line is initially flat, so its out-of-plane displacement position is 0. But then out-of-plane displacement from that is W. So the analog of what I just wrote down before is this now planar object that x1 maps to x1 plus U1 and W1 and W. Okay, its arc length element, G prime, so that's 1 plus the derivative U1. So that's G1, first component prime squared, second component derivative squared. So take the square root. And now I'm assuming that the derivatives of U and W are small, so I'll take the small slope approximation. And you see these two terms come in linearly because since you're expanding 1 plus gradient U, the leading order approximation is the mixed term. But here, there was no 1. And so the leading order approximation is quadratic. So G prime minus 1, I just subtract 1, and then I'm supposed to square it, and that's the expression I had. So the same calculation done in fully 2D setting produces a linear term plus a quadratic term, and the quadratic term is the rank 1 object made from gradient W. Okay, so let's use, yes?
On the previous slide, how can you, what's the justification for ignoring the quadratic U term compared to W term?
The justification is that in each case, I'm keeping the leading order contribution. So as you pointed out, in practice, what's implicit in this discussion is that you expect the gradient of W squared to be of the same order of magnitude as the first derivative of U1. And when that's true, then of course the other term, the quadratic term in gradient U would be smaller, right? It's a small slope approximation, so I'm expecting that these two terms are of the same order, and the term that I dropped completely is smaller. Now, I think maybe a related question is, how systematic is this? And the answer is, if you want to derive this as an approximation of 3D elasticity, it's actually it's not so well understood. There are ways of deriving plate theory based on 3D elasticity. But generally, either the membrane term wins or the bending term wins. And here we're going to be in a setting where somehow they're of the same order. Another version is to say, wait a minute. This problem captures, okay, here the membrane energy is non-convex, but in this small slope approximation, the non-convexity is somewhat simpler than it was otherwise. It's entirely due to this quadratic part of the approximation. So that even so it's generally true, I think, that once you've understood what happens from this linear framework, if you want to go back and do some more nonlinear picture, you've somehow got the right ingredients. Other questions? Okay.
Just maybe a mini one. So
Yeah.
you mentioned that the curvature term is regularizing perturbation.
Right.
Am I supposed to understand that because I know that the minimum is just flat and simple?
So that term, if you take the Euler-Lagrange equation, that's going to be the highest order part, fourth order, second order in the calculus variations problem. So it's going to produce a bilaplacian, but with a small coefficient.
It's over my head. That's okay.
Okay. You don't need to know that, right? Also, of course, okay, so the net story really is going to be that these terms, when we see these microstructures, it's because these terms are fighting with one another. In order for the first term, which is the dominant one, to be happy, you need some sort of a small scale pattern. Oh, but then the bending energy says, hey, you know, small scale patterns are expensive. Okay, so herringbones and labyrinths. The experiments that I'm going to talk about here, well, the experiment on the left, the schematic is at the top. You take some kind of polymer substrate, thick polymer substrate. You put it on a frame and stretch it biaxially. And then you deposit, well, in this experiment, gold, some crystalline solid on the top. The atoms have a preferred lattice structure, and they arrange themselves in a lattice. And then you release it from the frame, so it shrinks biaxially. And the atoms on the top suddenly experience that they're glued to, they're attracted, and they don't, in these experiments, remove themselves from the substrate. Oh, but suddenly they're crowded. It's like they got on the New York City subway and suddenly it's rush hour and there's not much room anymore. And if it were, if the compression, if the crowding were only in one dimension, if this were a schematic picture, then the film on the surface could oscillate. I drew a zigzag, but I guess it would really be a sinusoid. And by oscillating, it would make it so it stayed more or less glued to the substrate, but its arc length would be back to what it was before compression. And it would be pretty happy. It would experience some bending, and the substrate would experience some elastic deformation. But and to a leading order, okay, and so you can imagine doing that compromise. Oh, but the film has to achieve something similar to that that's biaxial, that's two-dimensional. And what you see is this herringbone pattern. It has two length scales. And the smallest length scale is quite regular and represents, I'll explain in a moment, something a bit like that. But it actually has a more complicated pattern. By the way, there's another way to do a similar experiment. Instead of depositing gold, you again expand the polymer substrate, and then you shine ultraviolet light on it. The surface of the molecules near the surface, they experience some reorganization because the ultraviolet light makes them debond, and then they can sort of relax to a polymer structure that's well suited to the expanded configuration. And then you let go of the substrate. The surface gets compressed, and in those experiments you see these are usually called labyrinths. Of course, different kind of an imaging, but this you see you're looking from above at a wrinkling pattern, which is, of course, I think the general opinion is that, pardon me, this is a disordered version of that one. I can't tell you so much about it because I don't understand it very much. Anyway, the story I want to tell you is about the one on the left. So the story I want to tell you is that a pattern that's sort of a mathematical caricature of this one. Well, I can't say it's exactly the minimum energy, but it achieves at least the minimum energy scaling law. That is to say, its energy is as small as it could be up to a constant in the scaling with respect to physical parameters. Okay, what are the physical parameters? Well, I take my membrane energy. Let's assume that, okay, I need to be able to talk about averaging of some kind. So I'm going to cheat a little bit. The real experiment is not periodic, but I'm going to suppose that on the scale of the experimental sample, I'll allow myself periodic boundary conditions. That's a scheme to allow averaging. And so I have, anyway, here I have the membrane energy per unit area, bending energy per unit area. Oh, there's a substrate. The film is glued to the substrate. So I have the elastic energy of the substrate. Here I just model, okay. I think when you think about solving Laplace's equation in a half space, you know you could do it by separation of variables. You use sines and cosines on the boundary, and then exponentials going into the half space. And the energy, the integral of grad u squared, winds up being a fractional Sobolev norm of the boundary condition. So you can do that for elasticity too. It comes out basically the same, and that's the model that I've used for the elastic energy of the substrate. And so that's a 1/2 order fractional Sobolev norm squared. But it comes with a coefficient, the alpha s. Well, since I had no elastic coefficients here, alpha s it gives me the ratio of the elastic stiffness of the substrate versus that of the film. I've normalized by the stiffness of the film. Oh, and what's up here? Well, unlike my piece of paper, this stuff, the film was crowded by the shrinkage of the substrate. It actually wants to buckle instead of my piece of paper. It needs to go out of plane. Why? Because it's trying to generate extra arc length, or more precisely, extra surface metric to make up for a compression of eta times the identity. So eta is the compression of that was produced by releasing the substrate from its stretched state, and the membrane energy wants, okay, if there were no in-plane displacement, then it would somehow be trying to oscillate out of plane in order to match, to achieve this extra stretching. And the problem, of course, is in one-dimension configuration you can do that, but the identity is not a rank 1 matrix. So that's not obvious how it's supposed to do that. So what was happening in that pattern? The answer, in the equation-free answer, is the following. Imagine you're part of the sheet. You're sitting there thinking about what to do. You're crowded. Okay, you know you could have sinusoidal wiggles in one direction, but that doesn't fix your problem because you're crowded in both directions. And then you wake up, you say, oh, wait a minute. I could deform myself in the same way that a square mapping to a parallelogram, when you map a square to a parallelogram in plane, you stretch one diagonal and you shrink the other. So I could experience shear, that's the mapping from a square to a parallelogram, in such a way as to make one diagonal happy. The other diagonal is even more compressed than before, but no problem because I know how to fix one-dimensional compression using wrinkling. All right? So you combine shear and wrinkling, and then you say, oh, but wait a minute, I'm attached to this big substrate. I can't just shear on a macroscopic scale. Oh, but there are two different ways to do this. You can map to a right, you can shear to the right or shear to the left. And so if you oscillate between them, then you have only a small amount of in-plane displacement, and you still fix the problem. So that's what's going on in the herringbone. As h goes to 0, optimizing this construction involves smaller and smaller length scales. And in general, this has two well-separated length scales. The smallest one is the scale of the wrinkling, and the larger one is the scale on which these two guys oscillate. Okay, but okay, I already said that guessing the upper bound picture, okay, it's a challenge. Actually, the physics literature had not found what I just told you. Okay, but the conceptual challenge is, how do you know you did a good job? How do I know that Tom won't come to me tomorrow morning and say, I have a better idea? How come the film doesn't do that? Right. And so you'd like to try to place some limits below on what's even possible. So here's how that works in this setting. It's very elementary. Let's set the size of our sample equal to 1 so I don't have to divide by it. And then the claim is that my membrane plus bending plus substrate energy, I can give a lower bound. The lower bound is the minimum of two expressions. The second one is obtained by the construction I just described to you, and the first one is obtained by the film just throwing up its hands and deciding that it won't do anything. U equals 0, W equals 0. It'll just experience compression. Okay, so the membrane term, it was tensor, the square of a tensor object, but I'll just use one diagonal element. I'll just use one part of the substrate term. And case 1. Suppose you don't wrinkle much. If you don't wrinkle much, gradient W is small in L2. Oh, then look at the membrane energy. Gradient W is small in L2. It's not playing much of a part. Eta is constant. And the derivative of the in-plane displacement should have average value 0. That's why I assumed macroscopic periodicity. Oh, but then constants are orthogonal to mean value 0 functions. So I'm assuming that you didn't wrinkle much. Mean value 0 function can't fix eta. This term is of order eta squared times h. Oh, now suppose you do wrinkle. Okay, well, let's see. There's bending energy involves second gradients. The substrate energy involves a fractional Sobolev norm, a fractional gradient. The membrane term involves the L2 norm of gradient. And there's an interpolation inequality. There are lots of inequalities like that. In this case, the L2 norm of the gradient, it can be estimated above by a higher derivative times a lower derivative, each chosen to the right exponent, so that you have a dimensionally balanced expression. Okay, good. So in case 2, this left-hand side is assumed to be of order eta. And so the right-hand side is at least of order eta. But it can be as this is like a geometric mean, and the elastic energy is like an arithmetic mean. And the geometric mean is less than or equal to the arithmetic mean. Oh, good. So the elastic energy plus bending energy plus substrate energy is bounded below by this. Here I did it this way. The bending from substrate terms is arithmetic mean greater than or equal to geometric mean greater than or equal to some expression involving gradient of W and L2 by this inequality. Oh, and we just assumed that that was not small. So in case 2, you get a lower bound from interpolation. This area is mostly like this. Lower bounds come from interpolation. And how else you use it? You've got this bending term with the small coefficient. You can only use it by combining it with other stuff. Okay, let's come to some more recent things. So here, this is different because the compression is achieved by geometry. I'm taking a sheet, a naturally flat sheet. I'm trying to wrap it around a sphere. Okay, and in this picture, let's say, so now we have a membrane energy, which is the familiar membrane energy of a flat sheet, bending energy. Here, instead of the fractional Sobolev norm, I just put an L2 norm for the substrate energy. It's more or less artificial thing that forces W would like very much to be minus x squared over 2r. That's the small slope approximation of a sphere. And in order to make that term strong, to make the sheet really conform approximately to the sphere, I put a large coefficient. I chose it to scale so that these two terms, the bending term and the membrane term, would interpolate to something of order 1. And so when they finish fighting, they'll produce an expression of order 1, which involves wrinkling, and which fights with this term. Okay, so you go through that, and the basic picture is that you'll get wrinkling that comes out of the fight between these two terms, essentially because if you imagine a circle in the sheet, it has to map to a circle on the sphere. Oh, but that's shorter. And so it wrinkles to avoid compression. Okay, so Peter Bella and I worked through that. We found the leading order energy and even approximately the leading order correction. The key feature here is, I left something out. Suppose a given circle in the sheet decides, why don't I stretch radially a little bit to I'll reach a little further down the sphere. It'll still be, the circle I'm mapping to will still be too short. But not as much too short. So the wrinkling energy gets improved by that, gets decreased by that. But you have some radial stretching as a result. And E naught, the leading order energy, is the compromise between the cost of stretching radially and the cost of, and the gain that the radial stretching gives by saving a little bit of bending energy. To us, the interesting feature of this problem is that the calculation I just described predicts a length scale for the wrinkling that's fixed independent of radius. But the lengths of the circles change in radius. So that leading order calculation tells you that the number of wrinkles at each radius has to change. And so it's the branching of these wrinkles, it's the sort of disorder or defects that come because the number of wrinkles at the outer edge has to be different from the number of wrinkles further in. It's modeling that produces this leading order, this order H correction to the scaling law. Okay, but I'm going to skip a little bit because I want to tell you about the last example. So this is work that Ian Tabasco did on the theory side after seeing some experiments and models that I would say were not so convincing by a couple of groups in the physics community. But here's the experiment. These sheets are not flat sheets put on a round object. Instead, they're curved sheets, shells, put on a flat object. Well, that's easy to do experimentally because water is pretty flat but permits a little bit of displacement of the surface. So they have a way of putting sort of liquid polymer onto a curved surface and using centrifugal forces to make it very thin, and then letting it dry. It dries to a very uniform film. And then they peel it off. They would cut a polygonal region or some shape region from the shell, and then they just put it on water. Surface tension pulls it flat. Oh, but the Gaussian curvature of the spherical shell and the Gaussian curvature of flat water are different. There's no isometry, so they have to do something because they're trying to achieve approximate isometry. And what they do is they make these interesting wrinkling patterns. These are pictures from the experimental paper. And you see you get fairly orderly wrinkle patterns, some regions more orderly than others. These were all made from the same shell, but with using different polygonal or approximately polygonal cutouts from the shell. And the pattern depends on the shape. Pattern depends on the cutout, even though you had the same. Okay, so Ian's success here was to model this by energy minimization and to really explain a lot about these patterns. He identified a rescaled energy that's asymptotically, it's the right asymptotic variational problem. And his asymptotic problem is convex, even though the original one was very non-convex. Oh, and so it has a unique minimum, unless it's very degenerate. And it turns out the convex dual has, okay, there's magic sometimes. Usually you can't solve nonlinear PDEs, but sometimes there's separation of variables. Okay, usually you can't solve convex variational problems, but sometimes using duality or something like that, you can, and this case is so. And that produces explanations to a large extent of these pictures. Let me give you some sense of how that goes. Okay, so a starting point is membrane energy, bending energy, and the gravitational energy of the water. It's the term that makes it try to be flat. Well, here, what's going on here? If your original shape was not flat, but was the graph of a function p of x, then the desired metric here, you go through the small slope approximation that I described before, you repeat it in that setting, and you find that the membrane term, obviously, what it would most like is that u equals 0 and w equals p, right? Because that's the graph that you started with. And if instead w were 0 because you were flat on the water, and then you say, is E of u equals to gradient p tensor gradient p? Well, the answer is no, because to be a strain, you have to satisfy some elastic compatibility conditions. It's the analog of a gradient has to be curl-free. And the function p satisfies those conditions only if the shell had Gaussian curvature 0. These experiments use a spherical shell. Okay, b plays the role of h squared before. I put it in different notation because what's really important is the competition relative correspondence between the term that's here and the term in front of the substrate energy. In these experiments, there seems to be only compression. So they said, oh, well, my work with Bella was looking in somehow the wrong regime. Surely you want B to be small compared to 1, but you want it to be such that when you interpolate between these two terms, that's going to give you something of order B times K. That should be small, so it doesn't somehow, so that this membrane term is still the dominant effect, instead of the two of them having to compromise. So B is going to 0, K is going to infinity. B times K should be going to 0, so that these two terms together still can't really compete. They still don't provide, they're still higher order compared to the membrane term. And then the claim is that the energy is of order, this energy, its minimum value, is of order 4 times the square root of B times K, with a prefactor that can be understood, because after you normalize, you get the minimum of this variational problem. Or in other words, if I renormalize this variational problem, I'm left with the task of minimizing this guy. Oh, this is just a constant. This is normal displacement over the boundary, so it's exactly a sort of an artificial surface tension. Oh, but your subject, remember up here, this is a constraint. Okay, gradient W tensor gradient W is rank 1 non-negative definite. If you see wrinkling, it means that maybe you have weak convergence here. So the weak limit would not necessarily be rank 1, but it would still be non-negative. And so the statement is, well, wrinkling, if E of U minus a half grad P tensor grad P is negative, you can fix that by wrinkling. If it's positive, forget it. And so we have a constraint, which is a matrix constraint. That's a convex variational problem because E of U enters linearly. The right-hand side is a known matrix valued function. And so this is like a, okay, the objective is a known constant times something linear in U. So this is, you would think of it as a semi-definite programming problem, except it's continuum. And as I think I just said, it looks like a surface. So somehow the terms in the energy conspired to create an artificial surface tension. And the asymptotic problem is that the in-plane, out-of-plane displacement is gone, because in the limit as our parameters go to 0, your wrinkling has smaller and smaller amplitude. But the in-plane displacement persists. We're studying the weak limit of the in-plane displacement, and it solves this. It looks like a surface tension problem, but with the constraint on stretching. Okay, and as I say, it's semi-definite programming problem. It has a convex dual. What's the nature of the convex dual? Okay, if you've ever studied convex duality, even linear programming, you know that the Lagrange multipliers for the constraint are exactly what you're finding when you solve the dual problem. And okay, so the dual problem is going to tell us where this constraint is tight or not. Oh, but it's a matrix constraint. So the dual problem is going to tell us, the dual problem is going to look, we're doing elasticity, so the dual, it's unknown, should be look sort of like a stress. It'll be a divergence-free vector field. And it'll be the Lagrange multiplier for this constraint. It can't be rank 2 because you can't have equality on a set of positive measure. That's this problem about elastic compatibility. But it could be rank 1. If it's rank 1, then it tells, oh, so if this constraint is actually tight in one direction and not in the other, that's one-dimensional wrinkling. So the solution of the dual problem, if you can find it, tells you the direction of the wrinkling. Okay, so following that path and solving the dual problem explicitly, Ian showed that in an elliptic, if the shape were elliptical, you would have one-dimensional wrinkling parallel to one axis. If it's a triangle, you would have parallel wrinkling near the corners. The theory doesn't. If the Lagrange multiplier is 0, that just tells you the constraint is not active, and it doesn't really tell you much else. So, in fact, in the white region, the theory tells you that that you don't have one-dimensional wrinkling, and in the experiments, that's where you don't see one-dimensional wrinkling. You see something more complicated. So where the theory predicts one-dimensional wrinkling, that pretty much maps to what you see. Where the theory says, I don't know, that pretty much maps to these somewhat more complicated regions, which, by the way, experimentally, you poke a wrinkled region, one-dimensionally wrinkled region, and it just pops back. You point poke one of these more complicated regions, and it doesn't pop back so robustly. So I would be happy to tell you more, but I think I should close. Ian's work is on the web. So let me instead sum up a little bit. Okay, so here, my entire talk has really been about wrinkling of a thin elastic sheet viewed as a variational problem, viewed as a challenge to try to understand so concentrate, it's wrinkling because there's a fight between the membrane term and the loads or substrate or other physical features of the problem. On their own, they would prefer some sort of small-scale pattern. The bending energy forces that pattern to have a finite scale and maybe resolves choices between different patterns. And the question is, how does that fight work out? At least, and what's the minimum energy as a number, and do we understand anything about the energy minimizing pattern? So that's somehow this class of physics problems viewed as a calculus variations problem. The examples that I discussed towards the second half of my talk were about either biaxial compression or geometry. And what's interesting about them compared, in the hanging drapes, well, of course the folds point down because gravity somehow organizes things. And the question is instead, what's that coarsening process? What's their length scale as a function of height? But in these more compressive or geometric problems, even the direction of wrinkling and will you see one-dimensional wrinkling or something more complicated is not so clear. These problems, a more traditional way to think about these problems would be bifurcation. But as I'm studying the behavior when the thickness is very small and the length scale of wrinkling is small, if I tried to do that by bifurcation, I would be looking deep in the bifurcation diagram at a parameter regime where there are a tremendous number of local minima, and I'm trying to understand which ones have lower energy. That's hard to do numerically or analytically as a bifurcation calculation. People do numerical simulations of problems like this. It's very useful. It's interesting. Of course, the simulation tells you what happens in the simulation. It still maybe only gives you a local minimum, and it only tells you what happens. It doesn't quite tell you why that had to happen. And so this is an attempt to get at those questions. And of course, I'm very keen on Tabasco's work because on the one hand, the wrinkling patterns that he explains were mysterious even to the folks doing the experiments. And because while what I described to you about, say, the herringbone gets the minimum energy up to a prefactor, oh, he even gets the prefactor. He gets an asymptotic variational problem. Thank you.
In the herringbone case where I think you didn't have convexity even asymptotically, if I understood that, how do you understand, or is there a theory of why there aren't lots of local minima that suck the state in as it's exploring around on its way to this minimum?
Great question. So, in fact, I think common opinion and my opinion about this labyrinth is that the system is getting caught in local minima, of which there are maybe many, and it just somehow finds its way to the nearest one and it's stuck. So a bigger puzzle is, oh, and how does it ever manage to do something different? And so that's been, there were some nice simulations done by, I think it was Zhigang Shuo's group at Harvard. They basically minimized, they did steepest descent on essentially this function, except, okay, they did steepest descent on this function, and they found labyrinths, which, in fact, in the simulation, they seem to gradually coarsen, so maybe they're not so much, maybe it's not about local minima, but also about sort of flat energy landscape. When they put in crystalline anisotropy, that is to say, they put in a Hooke's law here, reflecting the anisotropy of gold, that was enough to break the symmetry. And somehow that permitted it to get to this pattern, but there's no real understanding of why. Very natural question.
Question?
Very naive. When you wrote down that variational problem, you looked at it and said, that's not convex. I look at it and I'm clueless. Can you tell by looking at that first?
Well, of course, you knew it had to be non-convex because it's small slope approximation of something that's manifestly non-convex. But here the feature of, okay, in the physics literature, you would say you're doing essentially von Karman plate theory or something similar. The feature of this problem is that, okay, if you fix W, then you can easily find U just by solving an elasticity problem. But forget, suppose this were just gradient W, tensor gradient W minus a constant. So the family of rank 1 matrices is a very non-convex object. And in fact, the convex hull of this thing is, you can understand this, of course, but one can do that exactly. But that's maybe, I hope I've sort of answered that.
All right, let's thank Bob again.